Hello everyone. In this section, Principle of Superposition, we would like to talk about one interesting rule in this chapter, superposition. About superposition, in fact, this term actually represents the concept of adding something together. So you just add one together with two or more, okay? So how these things works in mechanics of material. Based on the definition we'd like to talk about here, it says uh, the resultant stress or displacement at certain point or at certain area can be obtained by the stress or displacement caused by each load component, acting separately on the member. So separately means you can derive the corresponding stress or displacement or strain from each simple loading condition. For example, like you apply something with two or three or more loads, moments, force on one component. In that case, the loading condition could be very complex. So in general, we cannot obtain good result directly from such boundary condition. In order to overcome this, principle of superposition says you can derive single stress and or displacement one single load at once. So you derive, for example, concentrated force at once, moment at the other, distributed load in the third. Then you don't need to worry about that complex condition. You just need to add these three cases, the result of these three cases together. Then you can get a good result without any problem. So this is a very helpful or very powerful uh, derivation derivation technology in mechanics of material. Similar process or similar idea can also be used in many other fields. So these types of idea uh, can be used in mechanics of material, of course, in the following complex problem. In these slides, we'll try to mention some basic assumption or requirements for this magic rule. Okay, so the loading in this case, first of all, loading must be linear, proportional to the stress and strain, and displacement, which means your input, for example, force or moment on the component, and the output would be stress and displacement, but you need to find them, you need to confirm that their relation should be linear. For example, like this formula, the force P and the stress are linear related. So when you increase the load as twice as before, then your stress will increase at the same time as the same ratio. That's what we talk about, linear relation. Similar things can be happen for displacement here, the load here, they also have similar relation. So that's case, you can, if this kind of relation exists, then you can use the superposition method, superposition principle to solve complex problem. The second thing is the loading must be significant change. Must not significant change. Okay, the original geometry or configuration of the member. Uh, why we need to satisfy this requirement? For example, this is a good example for this case. This is the cantilever beam under the downward force P at the end of the beam. So when this beam deform, they said the displacement of that or the stress of the cantilever beam can be derived by this at this. where P1 plus P2 equals to P. So this is the relation. But if the deformation of the beam, in this case, in these three cases, become pretty large, then you can imagine that the bending arm D won't be the same as D1 or D2. Okay? Then if that won't be satisfied, then your moment won't be balanced, which means P1 D1 plus P2 D2, because their bending arm are quite different, then the summation of them cannot be the same as PD. But your force is the summation of P, okay? P1 plus P2 equal to P. So in this case, the equilibrium or the balance of force can be seen in this case, but the moment cannot satisfy. Then you can imagine, in this case, the stress plus this stress won't be the same as this stress. Deformation have the same problem. However, in this book, most equations for load, stress, and displacement, the relation between them usually satisfy the linear relation. And in addition, the geometric change or configuration change for the topics in mechanics of material usually pretty small, sometimes invisible. So this type of problem in assumption 2 won't be a problem in our textbook. Of course, there's one thing we need to be careful: buckling. This is in the chapter 13. In this case, they may not be linear relation, so you cannot directly apply directly apply superposition method in this chapter. Next one, 4.4. This is another, or say, a new chapter, a new section in this chapter. It's called statically indeterminate axial loaded member. In fact, this section try to introduce a new type of problem we call statically indeterminate. This one, okay? Let's highlight this part. What's the meaning of static? Usually we said 静力, 静态. Indeterminate means cannot be determined. 不定, 无法确定, okay? So the combination of that, we usually say this is the so-called 静不定状态, 静不定问题. In this case, we need some special derivation process or solving process for these types of problem. So let's try to see one simple example in this section. First of all, this is the problem we'd like to talk about. First of all, we have a post in the middle of upper and lower boundary, which is from point A and point B are tightly fixed into the boundary. And then we apply a downward force at C, okay? The distance from C to A will be LAC, the other side will be LCB, the total length of the post will be L. Then in these types of problem, we can try to take the center part, the post, as a free body diagram, as can be seen here. So since we have two supports at A and B, then we will have so-called two unknown reaction loads, reaction force at this point, which can be determined or denoted as FA and FB. And for the free body diagram, equilibrium condition can only support or provide us single equation, which is the summation of force equals to 0 in the vertical direction. Although in two-dimensional system, we know equilibrium usually provides us three functions force balance in x direction or horizontal direction, vertical direction, and moment balance. However, in this case, all the applied load are so-called axial load, and they usually cannot give you any other additional equation in horizontal direction or so-called moment balance. Therefore, we only have single equation. However, if you check the unknown number, in fact, we have two unknown, but only one equation. So that means the equilibrium condition cannot directly solve these two unknown based on so-called force balance condition or balance condition. That's why we said statically indeterminate. 静力平衡 cannot be used at this time. 静不定 is the reason we call it 静不定. Okay, but how can we do it? How can we do to solve this? The way we try to do is we can use some additional equation from other parts of the problem or other types of condition. We call it compatibility or kinematic condition can be used. Compatibility 相容性 ，OK， kinematic 动态或者是运动 condition in this case, compatibility would be our choice, which means we'd like to use the condition of geometry, the constraint of the geometry to solve it. Where can we get this? In the upper case, we can use delta A over B equal to 0. What's the meaning of delta A over B? Which means with respect to B, the displacement of A should be 0. This special condition, based on the description, you know that there's no description related to force in this case. Actually, it's related to your displacement, which means it's related to geometry, deformation, this type of requirement or equation. So that's why we said, although we don't have enough equation from force side, moment side, but we can derive equation from geometry side like this. This kind of requirement actually obtained from our boundary condition because we already said A and B are static condition. We fix the post in their position. So based on the requirement of delta, load displacement relation can be used by this function, delta equals to PL over AE. The reason we can use this function because the cross-section of this one is constant. The length, yes, different part of that need different lengths. Area is the constant, E is the same material. So this is the first step for the compatibility condition. Next one, we'd like to use the previous equation to derive delta A over B. How to derive the total deformation from A to B or A respect to B? The process is quite simple. We need to solve the delta in two sections, AC and CB. The reason we need to solve that because based on free body diagram of section AC, we found that in that area, inside the section of A and C, we only have the internal force as the FA. The other part in CB would be FB. They have totally different internal force in each segment or in each part. So this one FA, this one FB, the length of LAC could be this part. AE are exactly the same. The other side would be LAC. The plus and minus sign, please be very careful. As we mentioned in sign convention in probably previous section, okay, we said If you have tension force, you need to add plus sign. If you have compressive force, you put negative sign. That's the reason we have plus and minus in each term. After we add them together, we know the final or the boundary condition of A at A and B require them cannot be moved during the loading condition. Okay, so we assign 0. Finally, we derive the result based on equation 1 and 2. The first one would be force balance equation. The second one derived from delta A over B equal to 0. Once we solve the unknown FA and FB, we got these two results. Okay, and you can see the final result of FA and FB. After we learn the solution of these statically indeterminate problem, like this one, we know that there are two types of problem in this chapter. First one, if your reactions can be determined by equilibrium equation, we said this is so-called statically determinate problem, which means you can use force balance or plus moment balance to solve all the unknown, no problem. You belong to the first case. Usually, the problem we have learned in before this chapter usually belong this part. But in this section, your reactions actually cannot be directly determined by equilibrium condition. Then we call statically indeterminate. This kind of problem needs additional equation from compatibility or from displacement geometry shape, like this. Here's an example for statically indeterminate problem. Example 4.4. In this problem, you can see that the boundary at A and B can be seen clearly over here, and there's a rod from A to B. Notice that there are a little gap, 0.2 millimeter between B and B prime. B prime is located on the wall. B is the end of the rod. Okay, then we apply a axial force P at C point C, this color C. Okay, to push it. Then we need to determine the reaction force at A and B prime. Then if the rod is subjected to a force like this, notice that we don't need to worry about the size of color at C. The Young's modulus is 200 gigapascal. In this case, actually, we may have two possible cases. One is after the actual loading, the point of P cannot contact point B prime, which means the gap's still there, but a little bit smaller. If that's the case, then the actual force at C would be exactly the same as the force or the reactions at A. Another case is when you push this rod at C, the end of B directly contact point B prime on the wall. So that would be the possible condition. The free body diagram for the second case, you will see that the applied load is here. The contact at A provide one reaction at A, but at B there's another, the second reaction at this point. In this case, if that is true, if we assume this is the correct solution, then we can use the equilibrium condition for the force balance in x direction. Then in this condition, minus FA minus FB means, based on the assumption of this balance equation, rightward direction is the positive direction, and all the leftward direction of FA and FB are all given as minus sign, and the applied load would be positive side. Then the summation would be 0. Of course, you still have two unknown FA and FB. The additional condition comes from compatibility. In this case, we assume the rod will finally contact point B prime. So we know that the movement of point B must be 0.2 millimeter. If you put this result over here, we said delta B over A won't be 0. It should be 0.0002 millimeter. Okay, so this is the special case based on the gap over here. Once we know the first equation and the second equation, we like to use load displacement equation to derive the detailed relation in the second equation. Delta B over A equals to 0.002 meter. This is the process. Since as we mentioned in the previous example, this delta equals to FA in LAC, FB in LCB. The relation of FA and FB can be derived by the free body diagram in AC section and in CB section. The minus sign means it's a compressive one. The other side would be positive one. Once we derive this, we substitute all the dimensions and the force and the constant into this equation. We got the second formula as function of FA and FB. Solving equations 1 and 2, we got FA equals to this number and FB equals to the other one. And it also mentioned that if FB has a negative quality, which means the problem could be statically determinate, and FB should be 0 and FA should be 20. Okay, that's the meaning of if we got something unreal, there's no contact at B and we only have negative quality, then quantity, then you can change to the other possible case we said in the previous slides, no contact. But in this case, we find that all belongs to positive, which means the second assumption is correct one. Okay, let's go to example 4.5. This is aluminum post reinforced by a brass core. So in this post, the external part, silver part, would be aluminum. This orange part or a little bit red part would be the brass core. Of course, a little bit stronger. And here we put a rigid cap on the top of that, so it's a rigid cap, and apply a force of 45 kilonewton. Then, after you apply force on that, we'd like to know the average normal stress in these two material, these two parts. The elastic constant would be 70 gigapascal for aluminum. The brass would be 105 gigapascal for brass. And equilibrium is like this one. The balance of force belongs to the summation of the support from aluminum and brass. So 45 equals to upward direction is positive, so plus FAL and FBR. This would be negative side because it's downward, okay? Of course, we still have two unknown. This is the one, the second, okay? So we need additional one by this special case. In this case, we know the cap applied force. They cannot determine how much stress or how much force applied on each part, but we know this cap will try to push them down in the equal displacement. Okay, that is the only things we can guarantee. So we know that this equation is satisfied. Delta AL equals delta brass. Okay, using the load displacement equation, we put the corresponding force, area, and elastic constant in each case, and they should be equal. Then we get the second equation. Solving the solution in equation 1 and equation 2, we got, this is the second one, okay? And then we can derive the force on the aluminum side will be 30 kilonewton, on the brass side will be 14 kilonewton. The stress on the aluminum side is like this, brass side will be this. So you know that although we put a small cross-section area in the middle of that, but it actually supports more stress than the other. Just like the force distribution, stress distribution in this plot. Here's another example, 4.6. In this figure, you have a steel bar, 3 steel bar, okay, A, B, C, D, and E, F. And these pin ACE link to this rigid member. Okay, so this part, the horizontal beam, should be know that it's rigid, no deformation on that part. And we apply a loading or downward force at the middle of B and A and C. So once we know this, and we use the equation for them, then we'd like to know what's the determine the force developed in each bar. Okay, that's the final result we'd like to derive. And also the question told us that A, B, and EF, these two parts, the cross section will be 50, and CD in the middle have smaller cross section, is about 30 millimeters square. In this question, we need to use the equilibrium to determine the force in each bar. Okay, so this is the beam applied force at AC, AB, CD, and EF, and the external force is like this. Then for this equation, we can derive two necessary equilibrium condition. One is the resultant force equals 0, moment equals 0. Then we get equation 1 and 2 based on the equilibrium condition. However, you know that there are 3 unknown, F, A, C, E. So we need additional one. What's the additional one? They said you can say, since ACE is a horizontal line, just like this, before the loading, after it applied the load at this point, although it may extend it in different lengths in each cases, but they should keep in a straight line, inclined line as A prime, C prime, E prime. So this relation can give us some geometric relation between each other. So this kind of case, based on the distance between delta A, E, and C, we can derive the relation like this one. Okay, delta A minus delta E equals to delta C minus delta E. And then we can derive the third equation. And about this part, we can talk about that in the next slides. This is the real relation between the delta at ACE. Notice that the smallest one we assume is located at delta E. The reason is we apply force between AC, so we assume this part will be moved downward a little bit more than the other side. Then next one, once we have this geometry, we put a horizontal line along delta E. And the remaining part will be delta A minus delta E and delta C minus delta E for the at point C and point A. And A prime and C prime, based on this triangular shape, we can use the similar geometry for the smaller triangle and the larger triangle and determine their relation. So delta A minus delta E has twice as much length as the other distance over here. So we just make this. This one is twice as much as this one. Once we have this relation, we can put in the equation and derive the third equation, Fc equals to this relation. Then finally, solve equation 1 to 3 simultaneously and use the force at ACE independently. Here's the other example. We call it 4.7. This example, is much complex than the previous similar cases. In this case, we saw that there's a bolt in the middle, okay? And then it is made by aluminum alloy and is tighted as it compresses a cylinder tube made of AN, magnesium alloy, okay? So here we have two materials, aluminum and magnesium, okay? And the tube has external radius. The tube external radius is like this one, is 10 millimeter. And it's assumed that both the internal radius of the tube and the radius of the bolt are both equals to 5. So you can imagine that this tube, external radius 10, internal would be 5, and the rod in the middle of that, or the bolt in the middle of that, would be 5. Okay, radius equals to 5. Notice that the wash at top and bottom over here are assumed to be rigid. So you don't need to worry about deformation coming from these two parts, and negligible thickness, so you don't need to worry about the contribution from the thickness as well. Initially, the knot is hand-tighted snugly. This means you just hand-tight, no significant deformation or compression coming from the setup at the beginning. Then you need to use a wrench to apply extremely large force to tighten it for 1/2 turn. 1/2 turn means for 1 turn means you rotate the nut for about 2 pi or a circle, and for a bolt the spec of that would be 25 threads per 25 millimeter. So if you rotate that to improve that for 1 thread, it moves about 1 millimeter. Okay, then finally determine the stress in the bolt. Okay, once we know all the requirement in this problem, then we can try to take or derive a free body diagram for this case. Notice that in this case, there's no external force on this system. Only the internal compression and tension exists in the rod and in the tube respectively. So when you tighten it, okay, we know that the external part will be subjected to compressive force, as we mentioned in the previous question. So Ft, tube part, will be compressive. For the rod, it's under compression. Then these two forces will be the same. So Fb equals to Ft, just like this. Although since we only have one equation but two unknowns, so we still need compatibility condition. In this case, we said when the nut is tightened on the bolt, then the tube will shorten as a value of delta t, and the bolt will be elongated due to tension by delta b. And since we know that the nut undergoes 1/2 turn, it advances for a value of 0.5. Since one thread gives you 1 millimeter advance, 1 millimeter displacement. In this case, you only move 0.5. But this one is a little bit tricky because 0.5 actually is coming from two parts. One is the shrinkage of the tube, The other contribution would be elongation of the boat. So combination of them give you this relation. Delta T equals to 0.5 minus delta B. Then, based on the knowledge we learned in displacement and load for actual loaded condition, we use the formula for delta T, the area of tube, material property, Young's modulus of the tube will be magnesium, and force and length 60 millimeter for the length. The other part for the bolt itself would be like this one, and sorry, the bolt is aluminum. Okay, the tube is magnesium. So bolt wise, area, Young's modulus, thickness, length, and the force itself. And this 0.5 represent the relative movement or the relative displacement between the bolt and the tube. Okay, so here we have a schematic plot to explain the relation we mentioned before. As you know, when you rotate the boat advances 0.5, just like this one. And this one actually can be derived from two contributions. One is the compression of the so-called compression of the tube, like this place. And the delta B will be elongation of the boat. They will balance and have a compromised position. That's the so-called final position. Over here, the final position is like here. Okay, so it's very similar, like you rotate that, you move forward to this place, but unfortunately your boat will be elongated and make the place from this point down to this place. Or you can say that you move forward to this place, but the tube also shrink during this process. So the real distance or real place would be still in the right line position. Okay, so initially it comes here, goes forward, back to this place. Okay, so that's the concept we get the equation in previous slides. Once we solve the equation for equation 1, force balance, the second one, the position of the nuts, we got the result for FB and FT as the same value, 30.96 kilonewton. Then based on the area of each case, we can derive the stress inside the boat and the tube. Of course, inside the boat, we got a pretty large internal stress. Okay, this is the normal one. Then we need to check if these two values exceed the yield stress of each material. The yield stress for aluminum, 414. For magnesium, it's about 152 megapascal. So these two values over here won't exceed them. This means this solution still in elect range. The process can be derived by the solution we mentioned in previous slides, and the solution over here